Welcome back to BiochemSerye Learning on the Go.
Yes, welcome back.
It's podcast 3C. Are you ready to talk about the reactions of lipids?
Absolutely, let's dive right in.
If you're just joining us now, be sure to check out the first two podcasts in this series on the structure and function of lipids, because that's going to be really important for today's topic.
Yes, it will. We're going to assume you've got those basics down so we can jump right into the reactions of lipids.
Because it's not enough to just know what they look like, right?
Yeah, no, not at all.
We need to understand what they do, how they interact, and why those reactions are important.
Precisely. And let me tell you, these reactions, they're happening all around us.
Oh, I believe that.
From the food we eat to the cells in our bodies.
Wow, that's fascinating.
Yeah, in fact, one of the most common lipid reactions is probably happening in your kitchen right now.
Really? Now I'm intrigued.
Yeah, think about it. Saponification.
That's saponification.
The process of making soap.
Wait, you're telling me soap making is a lipid reaction?
Wow. When you mix a fat or oil with an alkali, like lye, you know what happens.
What happened?
You trigger a chemical breakdown. The fat molecules get split into glycerol and the alkali salts of fatty acids.
Fascinating.
And guess what? Those salts, those are soap.
So every time I wash my hands, I'm witnessing lipid chemistry in action.
You got it.
That's pretty cool.
It's amazing how these biochemical processes are woven into our everyday lives.
That's so true.
And speaking of everyday things, let's talk about margarine.
Okay.
You know, margarine, solid at room temperature, right?
Right. Unlike vegetable oil, which it's often made from.
Exactly. That transformation, that's hydrogenation in action.
Hydrogenation.
Yeah, we're turning those liquid oils into solid fats.
So how does that work?
By adding hydrogen to unsaturated fats.
Okay.
Usually with a nickel catalyst, we can change their physical properties.
Oh, interesting.
It's a process that's used in a lot of food production.
Yeah, I could see how that would be useful.
But it does have its controversies, which, we can discuss later.
Okay, noted. Now, what about something a bit less appetizing?
Oh, what's that?
Rancidity. You know that unpleasant smell and taste in fats and oils that have gone bad?
Yeah, nobody likes that.
What causes that?
Well, there are two main culprits.
Oh.
Hydrolysis and oxidation.
Okay.
Hydrolysis is basically the breakdown of fats by water.
Okay.
And it's often aided by an enzyme called lipase.
Lipase.
Which is naturally present in many fats.
So they sort of have this built-in self-destruct mechanism?
You could say that. Now, the other culprit, oxidation.
Okay.
That's what happens when fats are exposed to oxygen. This process particularly affects the double bonds in unsaturated fatty acids.
Oh, I see.
And the result, those dreaded aldehydes that give off that rancid smell and taste.
So basically, light, heat, and moisture are the enemies of fresh fats and oils.
Exactly. And now that we've mentioned those double bonds, there's a test that can tell us just how unsaturated a fat is.
How many double bonds are present?
Exactly. You're thinking of the iodine number, right?
I am.
It's a key test for characterizing fats. It tells us about their degree of unsaturation, right?
Right.
And it can also be used to identify different types of fats and even detect if a fat's been adulterated. Like if someone's trying to pass off a cheap oil as a fancy olive oil, the iodine number can help catch that.
Like a fingerprint for fats. That's fascinating. So what other tests do we have in our lipid detective toolkit?
Well, we've got the saponification number.
Saponification number.
Yeah, and you might have guessed it relates back to that soap making process we talked about earlier.
Right.
It basically tells you how much potassium hydroxide is needed to saponify 1 gram of fat.
Okay, and what does that reveal about the fat itself?
It's inversely related to the molecular weight of the fat.
Interesting.
So fats with shorter fatty acid chains will generally have higher saponification numbers.
Oh, okay.
Another test, the acid number, measures how much potassium hydroxide is needed to neutralize the free fatty acids in a fat.
And that tells us?
It's essentially a measure of rancidity.
So high acid number equals rancid butter. Yuck.
Exactly. And finally, we have the Reichert-Meissl number.
Okay.
This one measures the volatile fatty acids distilled from a sample of fat. This one's particularly helpful in distinguishing butter from those synthetic substitutes.
Wow. So each of these tests provides a unique piece of information about the composition and quality of a fat.
Absolutely.
They really help us unlock the secrets of these complex molecules.
They do. They really do. And understanding these tests, it's crucial for anyone working with lipids, from food scientists to biochemists.
Okay, so we've covered a lot of ground on lipid reactions and how we characterize them.